Started now, my name is Jay Hannon. I'm IBM's University Relations and the chair of the session. Before I introduce the speaker, Stuart Long, I'd just like to give one little housekeeping note. Are any of you attending the dinner this evening? All right, here we go. If you haven't heard already the instructions, there's a bus that's going to take you. The bus will be leaving for tonight's conference dinner, and will be leaving at 6 p.m. outside of Bridges World Square Hotel on Pitt Street. That's about 1 block away from here. And that'll take you to Dalton House where the dinner is. So please be there 5 minutes before 6. So again, that's Bridges World Square, Pitt Street. I guess also I'd like to ask if you could please turn your mobile phone off. Particularly you, our previous speaker, his phone would off right in the middle.
Learned from experience on that one.
I'll just very, very briefly provide a little background, if I can, on Stuart. Stuart is Chief Technology Officer and Senior Director of Systems Sales Consulting for Oracle Systems throughout Asia Pacific, and certainly including Australia, obviously. He leads a large team of architects and consultants who are working with clients in the telecommunications area, finance, manufacturing, government, and very, very much so within the research community. So they have terrific expertise in this area, and we're going to hear from Stuart today a very interesting presentation, which I'm sure you'll find very worthwhile.
Thanks very much. So, small crowd. Hopefully I'll get through quickly, give you guys a chance to ask some questions at the end. So please feel free, to take some notes or to come back to me at the end and ask a few questions. So what we'll do today is really go through what Oracle is doing to create a different type of architecture or different type of systems, really around the information capability models that we're bringing to the research environment. And what we believe is that, data is only one part of that model. And what you'll see today is how we're basically doing the people, the process, the tools, a lot of that around how you can start to classify your data, how you can then start to create communities around how you can use that. So this goes into things like identity management, being able to make sure that the data is presented correctly. So do you present the raw data? Do you just present the analytics from that data? And moving forward, this is becoming the key as to how we can create these sort of sharing networks across very different environments. So as we break out from that, really just looking at the information architecture, there are many things around this. So Oracle has developed a number of different platforms that you'll start to see coming out. One of them is the Oracle Social Network, which you can now basically plug in to a lot of the Oracle products to start to be able to create your own communities and share your data around these tools. And the key here is it is integrated from the base product up, so it doesn't matter where you're wanting to share the raw data, whether you're wanting to share the analytics, you can basically create these communities, you can have identity management, you can basically have security, you can have profiles around this data to ensure that what you're sharing is basically being seen by the correct people and being used correctly. And what we'll talk about today a bit more is really around unstructured and big data. So Oracle's been around industry for quite a while around the information, started off the heritage of database. So we've got a pretty good understanding of master data, reference data, metadata, transaction data, which is really sort of the core of most data models today. What you're starting to see is how we're building analytics into the data model itself and how we're changing the nature of analytics by using different technologies which allow us to basically store information in memory and do what used to take hours now in seconds. And this is fundamentally changing the way we can start to bring research to the fore. So instead of having to wait days or hours for analytics to come back, we can now start doing that in seconds. So the number of models, the number of permutations we can start to look at becomes quite vast. The big area of growth really is around the unstructured data, around big data. And this is where customers looking at this as really that next level of competitive advantage. So how can you basically start to look at not only the data itself, but how the data was captured, information around that, to start to work out why results are different or how we can start to influence these results by understanding how and why the data was collected. So again, typically what we're starting to see today around big data is a whole range of solutions. Sensor data is becoming more and more prevalent. So these days, the amount of sensors you have, the capability of those sensors to capture data, is becoming huge. It's becoming basically a tidal wave or a tsunami of data, as they say. And so some of this data is structured, some of it's semi-structured, some of it's unstructured. So how do we manage all this data? How do we bring it together and start to get some understanding on the whole solution? And what you'll start to see is, especially in the field of research, this stuff is becoming, the biggest problem is storing the data and making sure we can relate to it in the future. And what we're starting to see is the ability now of these sensors to produce petabytes worth of data a day means that, now the needle in the haystack is becoming even harder to find. And so what we're starting to show you is how we can take this data, we can now start to store it in a more economic way, understand its value, search it, analyze it, and then keep it in formats which allow you to do the best post-processing on that data capable. Some of the challenges we said are the volume. So the volume of data is growing and growing very rapidly. If you look at the genome sequencing, what they're saying is the amount of sequences they're finding is going to outstrip CPU and disk technology in the very near future. We'll actually be creating more data than we're capable of storing. So how do we start to do this more and more efficiently? We'll talk about things here around compression algorithms, which allow us to take hundreds of terabytes worth of data and start to compress them into only a few terabytes. We're talking in some of our solutions up to 50x type compression on that data, understanding how it's stored, understanding the best way to keep that data. We then look at the velocity, so how quickly this data is being created, and how we need systems that are basically built of different technology to be able to keep up purely with just the data capture rates that we're starting to see in some of these areas. We then talk about the variety and say this is where we're looking at the different types of data, how we can then start to basically keep all of these solutions in a single repository, but then start to make analysis of the different characteristics we're seeing in that data. And the last one is the value. So a lot of people are saying, this is great, let's just capture all this data. The problem in capturing data is it has a cost. And therefore working out what the cost-benefit analysis is and a lot of this becomes very, very difficult. So what we have is solutions that allow you to look at the potential value, to classify this data, and then start to see how often it's accessed. And we have solutions, I think we talked about previously, around how we can move that between different tiers, etc., to basically maintain the value of that data. What we're also seeing is how we're changing the solutions around how we capture this data. So this started happening a while back. Intel started doing this a while back, where they started to look at how they could make solutions more efficient. It was always very simple to write software, so virtualization was a classic example, where we basically wrote a software layer, put it on top of hardware, and people said, well, that was wonderful. The problem was it came with an overhead. And so how we basically fixed the virtualization problem was we started to take the software and build it into the silicon. And what you're seeing from Oracle is basically the same thing. So what we're doing is taking Oracle software, we're basically taking our IP that we have around that whole data stack, and we're now starting to build that into our silicon. And what this means is the silicon now understands much better data types. So we're not having to do these conversions between the various different levels of data at the silicon layer. We're building that and baking that in. And so what you're now seeing is really a data processing unit. It understands SQL, it understands data structures. And what we're seeing in simple things like Oracle numbers, this is the way Oracle stores numbers in its database format. We're seeing a 500 times performance boost because we're actually building that technology into the CPU itself. What we're then doing is understanding where we're storing that data. So unlike the disk-based players, we're actually saying the best way to classify your data is at that application level, understanding what the data is. When you understand what the data is, then the application can store that data where it best makes sense. And this is where you'll see multiple tiers of storage. We can talk about cache, we talk about memory, we talk about tier 0 disk now being solid state, we can talk about tier 1 disk, around how you can then place that data where it needs to be based on application requirements, not based on how it's accessed. And then we can understand how that data is used across the network. We can start to create what we call data-defined networks, where understanding the protocols, understanding the data sets itself, we can prioritize that data to allow us to ensure that if we are capturing streams of data, those streams of data are prioritized correctly and captured correctly, basically from a network level. And all this basically starts to go into making solutions which are additive. So when we get a 10 times performance boost on the CPU and a 10 times on the memory, you're starting to see solutions that start to be 100 times more performant than our competitive solutions out there. And a lot of this is really allowing us to move to what we call the real-time data analytics. So with all this data being created, you're almost moving to the point where you need to start to capture and classify this data in flight. It's no good just to continue to store huge amounts of this data in the hope that you'll be able to process it at a later time. And so we're building sort of real-time technologies which allow you to do this complex event processing at basically the time of capture. And we're doing this now because you're seeing a whole different range of technologies that are basically allowing us to do this basically in real time in memory. And what you're seeing here is the ability for these solutions to basically store it at these different layers. The reason why we have the graph looks very nice, it looks nice and linear, but when you actually look at it on a logarithmic scale, the performance difference between real memory and tier 1 disk, which is what most people use today, is about 160,000 times different. So therefore, storing and manipulating data in memory is 160,000 times faster than doing it on disk. And so understanding where you want to keep that data, how you want to manipulate that data, means we can now start to store at the various different levels. And all this is great, you say, but you say, well, main memory is volatile. If I lose the power on that box, I lose that information. Again, there's some information that, quite happy to live in with that volatile environment. We now have these DRAM memory appliances. These are basically cards or boxes, and they have battery backup. So they're good now for about 72 hours, how you can keep that data. And then we have a whole range of disk all the way to nearline storage about how you keep that data and basically being able to load and transform that data as required. So this is really what is changing this environment, how we start to build these different types of systems. So what we're saying is now, when you're looking at one of these solutions, it's no longer how much CPU, how much disk, how much memory. It becomes three-dimensional as to what you are doing, understanding what the outcomes are, and then how we can start to design these solutions for you from the ground up. As I said, Oracle has basically built an architecture around this. So as you start to do these building blocks, you can just plug in identity management, you can plug in social networking, you can plug in real-time analytics into these solutions and basically do it in a very framework-based, componentized way. What we'll talk about today is some of our solutions. You heard about big data appliances. These are running Hadoop. What we're doing is basically building what we class as engineered systems, which are specifically designed to run these tasks. And what we can see here is we have devices now which are really there to acquire and organize different data from different streams, basically very, very high performant, linearly scalable. So as you need more requirement, you just add more boxes, connected to high-speed networks, which allows us then to basically do all of this on the fly, then start to basically store it in our data warehouse type solutions in an Oracle Exadata, keep that data there, and then basically organize that data and move it to a visualization platform where we start to talk about in-memory databases, storing that data totally in memory, compressing it 10 times, so a terabyte of RAM becomes 10 terabytes of usable storage, and then being able to analyze it basically at what we class as the speed of thought. So there's a number of different things I'd love to talk to you about. I could go for hours. What we'll try to do today is really have a look at the analytics piece. There's a whole research data management. There's a whole research administration and control piece, which basically fits into what Oracle call is really the research enterprise. And so we've built these products similarly to what we have with our enterprise products, specifically for research, understanding the struggles you guys are facing, and hopefully showing you some of the solutions we're bringing out to do this, specifically around the analytics part today. So what we're starting to see here really is the platforms enable you to work collaboratively on extremely large sets of data. And so what we're seeing here is, depending on where you want to share that data, we can now give you that ability to share the raw data, how the data is being captured, including the metadata, or the visualization or analytics of that data can be shared as well. And again, based on our platform with identity management going through the whole solution, you can now start to share this basically on the Oracle social network, create communities around the research, and start to be able to do this, as I said, in near real time. The benefit here is as you start to classify and move that data into the visualization space, then you can share that data far, far easier. and all the work is being done, and basically a lot of the volume basically goes out when you start to visualize that data. We're also basically having frameworks here to allow you to build workflows. So these workflows can be captured and published, so people can not only see your visualization, but they can also see the way you've got to your visualization. And you can now start to look at ways of basically capturing, optimizing, and sharing the workflows around how you're working on this data, how you actually came to these conclusions built on these data sets. And then people can basically adjust or change your workflows, run them against the same data sets, and see what their results would be based on those changes. And then we can basically plug this into a whole applications framework that allows you to basically take what is raw data and really turn it into information, which basically can then be loaded, changed, evaluated in many different formats. Many challenges we see here, the exponential growth in data. As I said, what we're starting to see is how we can do compression. The key here is we're doing compression at the data storage layer. So what we're doing is being able to compress and store our data in that same format. And we're actually building the compression algorithms into our silicon as well. So what that means is our storage systems, our compute systems basically don't have to, compress, uncompress this solution every time they actually look at the data. They can basically move it around compressed, and there's a huge benefit in how we can do that. We can look at how we can start to accommodate the new data sources we're starting to see coming in through the different type of sensors we start to see being created, how we can start to merge that with existing data sets through our acquire and analyze phase. We can start to become more predictive, and we can start to do real-time analysis. So we just saw that there was a tsunami warning in Hawaii, and they basically cleared most of Oahu and tens of thousands of people. And the wave ended up being about 2 feet high. So these are the different things that we can now start to pull together and do real-time analytics basically on what we see and what we see coming forward. As I said, we've got a whole solution around this. I won't go into all the different pieces, but really creating that whole ecosystem for you to basically show you how you can capture, share, evaluate all these solutions all the way from the sensor all the way back through to the storage layer. We can talk about organize, discover, visualization and sharing, which is typically the process we like to talk about as we go through our analytics flow. The key here is we can do this at high velocity. We're using high performance networking. We're doing a lot of in-memory storage. We're basically writing now to cache. So what that means is it's basically instantaneous rather than having to wait for spinning media underneath. It's all open standards. So the whole idea here is it's all Java, all SQL-based interfaces. It's using R, it's using Hadoop. So it's using all the same tools and features you're used to today. We can have all the map reduced. We've got all the statistical tool sets, and we're actually building these tools into the database. Again, these are part of the database structure and not additional tools which basically then try and leverage that underneath. The visualization allows us to basically take these loads, move it into a more visualized format, and then allow you to share that, reducing the number and the amount of data and being able to have very large data sets in a very visual type environment. And then sharing, as I said, we've got the Oracle Social Network. The whole ability here is to create communities around the research, around the data, to be able to do this for you. Quickly just going through some of the stuff. As I said, all open standards, HDFS, NoSQL, Hadoop, in-memory analysis, all the way through. We're just running out a bit of time, so I'll go through it quite quickly. What you're seeing here is, again, a number of different capture from multiple different sources, how we can then organize it and basically then share it. We then have this information discovery tool, which allows you to sort structured and unstructured data and create a different way of looking at and using that information. We have the big data appliance. We have the Exadata for the data warehousing. We have the advanced analytics built into the database. And then we have the Exalytics, where we're taking this information, storing in memory, using in-memory database to allow you to do the analytics on it. So all tightly integrated, all in a very high performance backplane. We have a number of customers, happy to share more information with you, running out of time. Want to ask a few questions. Thank you very much.
Very good. Thanks very, very much, Stuart. question. Any questions that anyone would like to raise? If not, I'd like to thank you again very much
Thank
for
you.
doing this. Thank you for joining us, everyone.